All right, so I'm going to hide that heat map for now and bring back our point layer. And again, make sure that you are in Mercator. Sometimes it switches back for whatever reason. Just make sure you're still in it. And now I'm going to go to Raster Analysis Grid. Okay, and this is an interpolation. It's similar to this. This is a basic interpolation. It just has one kind of control. This will let us control the parameters of that interpolation much better. Okay, so I'm going to click on Grid. It's going to ask for the input file again. I'm going to select our food project file. And for the Z field, this is the data you want to work with. It's the data you actually want to interpolate. Okay, so if you're doing topography, Z is actually height. If you're doing any other data, you can just think of Z as the other dimension, right? So you have latitude and longitude, X, Y, that's spatial data, and you have some other data in the Z field. When we do these interpolations, we're going to create conceptual topographies, which interpolate the actual height of that field. Okay, so I'm going to pick my check-ins. And in this case, if we hadn't done that step of converting this to a number file, you might not see this. This will only display numerical data. So you might have to go back and change that, convert it to a numerical field. For output file, we're just going to specify a file name here. Let me see. This is a different file type. It's a GDAL, general file. Don't worry about the file type too much. I'm going to call this interpolation. Save. Okay, and it's just like before, there's a few parameters that basically control the way that this is going to look. And a lot of times there's not too many rules of thumb. You're just going to have to play around with these parameters until you get the effect that you want. Okay. So we're going to check algorithm. This is going to let us specify the algorithm we use to do the interpolation. For these purposes, and in almost every case, you use the inverse distance to a power. This is the basic interpolation algorithm. You can mess around with the other ones, but this should be the default. That's what we're going to use. The inverse distance to a power does a very similar thing to heat map, but it's going to take every pixel in our map, so every analysis point, and it's going to look at every other point in the map, and then calculate the sum of the values of each point. So if in this case, we're going to look at check-in number, right? That Z value. It's going to take where the point is. It's going to look at every other point and then multiply the value times the distance from that point. And this is the way that it weights things that are closer. It weights them more. So it considers every single point, but it's going to take more and more of the values of things that are closer to it. The basic idea is that each point is just going to be more influenced by things that are around it. And the power in that inverse distance to a power specifies how it weights that distance. Okay, by default, it's going to square that distance. So things that are closer to the pixel will be a lot more important than things that are farther away. Basically, it just means that the fall off becomes a lot steeper. That's as much as you need to conceptually think about it. Just like with heat maps, I said, this results in a bigger number of smaller hotspots. Same thing here. The higher the power, the more localized your interpolation is going to be. The lower the power, the more spread out it's going to be. In this case, because we have a lot of points, like one thing that's getting a lot of check-ins might be right next to something that's not getting any. If you use a very localized approach, it's going to create a very bumpy map, and it's not going to be that useful for analysis. Okay. So in this case, because I've kind of played around with this with a lot of different values, I realized that we need a more distributed approach. I'm going to lower this power value. Okay. And I usually work somewhere between 2, which is a square, to 0.5, which is the square root. Okay, and then some of these might be useful to play around with. This grid interpolation tool gives you a lot of control over all the parameters of the algorithm, but the only one that really matters is this one. So the next thing we want to do is these two fields actually specify the size and resolution of our map. Okay, so resize will be the resolution of our image. Okay, so just like before, we were dealing with something like 500 by 500 pixels. I'm just going to specify that here. So in this tool, you can't specify the exact size of each pixel, but based on your aspect ratio and the resolution, you can get something like what you want. So I'm going to say 400 pixels wide and 300 pixels high. Interpolation does take longer. It's a more complex algorithm, so be careful with these. Okay, you don't want to do too high. It'll take forever to process. And the extent will be the actual boundary of our raster. Okay, with heat maps, it generates it automatically based on the extent. Here you can enter the values, or you can drag on the canvas itself to specify it. So the easiest thing to do is go back to your map and just drag out a border capturing all of the points. Okay, you can see here it's brought in those values automatically. So now I've specified the size of my raster and the resolution. It's going to be 400 pixels wide by 300 pixels high. Remember, each pixel is now a data point that processes something about how these values change over the geography. And click OK. So this does take longer. Now it's completed, and I'll click OK. You can see the heat map or the interpolation here. It's very similar to what I showed in my examples. Okay? You can see also how it's spread out the interpolation because I used a lower coefficient for the power. Just to show you the difference, I am going to make another interpolation and change this back to the default power. This is square, right? So it's going to take the distance inverse and square it. It's going to privilege points that are nearer a lot more, so it's going to localize that analysis. So I'm going to keep everything else the same, click OK. This is actually much faster because it doesn't have to do as much calculation. And now we can compare the two analyses. Okay, this is our first one. This is taking the square root of the distance. You see this big void in Hong Kong, this big hotspot in the center of Shenzhen. And then compared to something like this, which is just a lot more localized. But you can see at this resolution, this fine grain interpolation between things that are very low in check-ins and very high, not that useful, okay? And there's no sort of theory about what's right. It's based on your analysis. These interpolations are really supposed to help you hone in or communicate something about your data set, all right? So if this doesn't look like it's that helpful, you can always try to change the resolution of the analysis. Okay, so we can visualize this the same way. Go to single band pseudo color. I'll pick the reds here. Okay, so we visualized it here. I'll bring back my water boundary. And there you have the two basic maps I showed. Okay.